Create a function by composition of functions. Performing algebraic operations on functions combines them into a new function. But we can also create functions by composing functions. When we wanted to compute a heating cost from a day of the year, we created a new function that takes a day as input and yields a cost as output. The process of combining functions so that the output of one function becomes the input of another is known as a composition of functions. The resulting function is known as a composite function. We represent this combination by the following notation. So you have f, this now open circle is called composite. You would say f composite g of x, which is the same thing as f of g of x. Now, we read the left-hand side as f composed with g at x, and the right-hand side as f of g of x. Now the two sides of the equation have the same mathematical meaning and are equal. The open circle symbol is called the composition operator. We use this operator mainly when we wish to emphasize the relationship between the functions themselves without referring to any particular input value. Composition is a binary operation that takes two functions and forms a new function, much as addition or multiplication that takes two numbers and gives a new number. However, it is important not to confuse function composition with multiplication because as we learned above, in most cases, f of g of x does not equal f of x times d of x. So again, that circle doesn't mean multiplication, it's composition. It is also important to understand the order of operations in evaluating a composite function. We follow the usual convention with parentheses by starting with the innermost parentheses first and then working to the outside. In the equation above, the function g takes the input x first and yields an output g of x, and then the function f takes g of x as an input and then yields an output of f of g of x. So, in the composite function, when we write this definition, g of x is the output of g is the input of f. So x is the input of g, and then g of x becomes the input of f. Now in general, f composite g and g composite f are different functions. In other words, in many cases, f of g of x does not equal g of f of x for all x. We will also see that sometimes two functions can be composed only in one specific order. So let's take a look at an example here. It says if f of x equals x squared and g of x equals x plus 2. So in this composite function f g of x, I want you to pay close attention to the input. Now the input is g of x. Well, what does g of x equal? Well, it equals x plus 2. So we're going to replace g of x now to be x plus 2. So now this x plus 2 becomes an input on f of x. So this x plus 2 is now going to replace the x, and then you're going to square it. So you can see here now this x plus 2 is then squared according to our f of x function. And now when we square that, we get x squared plus 4x plus 4. Next, we have fg of f of x. So what that means is f of x becomes the input. Well, if you take a look here, f of x represents x squared. And then what we're going to do is we're going to replace this x squared in for the input x into the function g of x. So now this x squared is replacing this x to get x squared plus 2. So if you look at these two expressions, okay, they're not equal for all values of x. So the two functions are not equal. It is irrelevant that the expressions happen to be equal for the single input value x equals negative 1/2. Note that the range of the inside function, the first function to be evaluated, needs to be within a domain of the outside function. Less formally, the composition has to make sense in terms of inputs and outputs. So, composition of functions. When the output of one function is used as the input of another, we call the entire operation a composition of functions. For any input x in functions f and g, this action defines a composite function, which we write as f composite g, such that f composite g of x is equal to f of g of x. The domain of the composite function f composite g is all x, such that x is in a domain of g and g of x is in a domain of f. It is important to realize the product of functions f times g is not the same as the function composition f of g of x, because in general f of x times g of x is not going to equal f of g of x.